Hey everyone. First, let me introduce myself. My name is Emily Peterson. I'm a assistant professor here at Emory University in the Department of Biostatistics and Bioinformatics. And I'm going to talk a little bit today about the research that I do. So, looking at this plot, if we see data that we observe, so the data that we observe are denoted with the red dots. The question that I try and answer in my research is what happens if we know that the data that we observe is error prone or very biased? So in the blue, we have the true association between X and Y. So X is on the X axis and Y is on the Y axis. And this is the true association. But what we observe is the data in red. So the question that I try to answer in my research is how can we uncover this true association, knowing that the data are very biased, but we don't know what this true association is. So the truth is unknown. We just know that the data are not well equipped or limited in being able to capture it. This area of research is known as measurement error. So the way that we try and answer this in my particular research and in my projects is combining a few different methods. So one is in Bayesian hierarchical methods. This combines prior knowledge and observed data with a probabilistic framework. And our goal is to produce uncertainty-aware estimates, meaning we are able to quantify the uncertainty around the estimates for small or sparse populations when we're using error-prone data. The second type of methodology that we incorporate is measurement error methods. So this adjusts for bias in reported data when we know what kind of bias there is. So this can include things like misclassification, misreporting, missingness, sparse data. We're able to adjust and correct for the error that's in the data if we have some sense of the extent or the degree of that bias. Lastly, a lot of my models, because I work in small area estimation, incorporate spatial temporal mapping methods. So this is when we account for the spatial and or temporal correlation patterns across different units. So we can identify local patterns in granular units over time. Lastly, a lot of my work is in population health research, and so this is a subset of statistical demography, meaning when we want to account for population structures and changes and dynamics in the population, we have to accurately measure what's actually happening in the total population. And then we can also focus on a particular health or mortality indicator. When you focus on population level changes, this refers to statistical demography. So I'm going to talk about a couple of projects that I'm currently working on, so I give you an idea of the type of work that I do. The first is data integration methods for estimating small area American Indian and Alaska Native mortality outcomes with measurement error adjustment. So this plot is quite busy, but what I want you to see is that there are three ways to define what American Indian means in the United States. One is through tribal enrollment, meaning someone is a registered citizen of a particular tribal nation. Sometimes people self-report as American Indian on census forms or state or federal forms. So that's self-identification. And then lastly, because tribal nations have delineated geographic boundaries, people can live on or off tribal lands. So that's a geographic classification. So when we want to build a tribal mortality surveillance system, we want to report on these three different descriptions of American Indians. But there's a big problem. The big problem is that in mortality data specifically, and in health data, that there's a huge amount of misclassification error in those data. So American Indians, on average, are racially misclassified 30 at a rate 30% more than any other racial group. So if you just take that raw data and use it to say something about what's happening to American Indians, you're severely going to underestimate the burden to the American Indian population. So now we know that the data is very error prone. We want to develop methodological approaches to assess county level temporal trends in cause specific mortality. And we want to be able to build data science tools so that we give tribal nations a suite of resources to accurately and comprehensively monitor mortality in their population. So we combine the different methods that I described earlier, Bayesian hierarchical methods, spatiotemporal mapping, measurement error methods, to build a suite of tools and model-based estimates for tribal nations. What we're going to do is we're going to collaborate with Cherokee Nation Public Health, CNPH, to develop these methods and data science tools to be able to strengthen their local mortality surveillance. We're going to produce these estimates from 2020 to 2025 for the three AIAN descriptions that I described earlier. So this, in essence, builds a tribal-led mortality surveillance system that has never been done before. The second project I'm going to talk about is Bayesian reconstruction of the under 5 small area population, correcting for undercount bias and source uncertainty. So the under 5 population, these are children under 5 in the United States, are the most undercounted population in the US Census. Approximately a 5.4% net undercount, which means there's an undercount of over 1 million children in the United States in 2020. Why these undercounts happen is that the under 5 population does not show up in very granular, detailed, and rich administrative data sources like school records. They're not in school yet, so they're harder to capture. And what we do know is that undercounts vary systematically across geography, household, and social vulnerability, particularly for rural counties. So our goal is to create a model that produces a more accurate estimate of under 5 population counts at the county level. To do this, we're going to, again, combine Bayesian hierarchical data integration with measurement error and bias adjusted methods to produce county level estimates. So you don't have to memorize this plot, but this plot just kind of shows you the type of models that I build with the collaboration of my colleagues and my students. So we have a model here that models the number of births, the number of deaths, and the number of migrations among the under 5 population. But each one of these is a parameter because we don't know what the truth is. We know that the data is biased. So in order to estimate the under 5 population, we have to build model structure into each one of these parameters. We combine data from the census as well as birth data, death data, and net migration data to inform this model and the model-based estimates that it will produce, as well as the model structure that we include within our Bayesian hierarchical framework. So those are just two of the projects that I'm working on now, and I also have others, and I will send you or give you a QR code at the end so you can see what other projects are available. But I also am a mentor and teacher here in the Department of Biostatistics. So currently I teach the BIOS 526 class, Modern Regression Methods. I also really enjoy mentoring master's and PhD students in Bayesian spatial hierarchical modeling as well as measurement error models if they have an interest in building these types of models that try to produce accurate information in the context of bias and sparse data. I also serve as a reviewer for journals in biostatistics and spatial epidemiology. So in addition to my research, I truly enjoy working with students And there are multiple projects, if you're interested, that you may learn about or join. If you're interested in the other projects that I do or just reading more about the projects that I presented today, here is a QR code. You can also email me at emily.nancy.peterson@emory.edu. I would love to talk to you. Or if you have an idea that you think may fit into what I do and you would like some advice or guidance, please do let me know. I'm happy to learn more about the topics you're interested in. Thank you.